Hello all of you. Welcome to the 47th lecture on the course on analysis and modeling in chemical engineering. In this week, we started discussing about separation processes and we discussed some basics of separation processes in the previous lecture, and we ended up discussing about some thermodynamics of separation in terms of the idea of phase equilibrium, basically something that we have discussed long back in the course, but we discussed the language of the fugacity coefficients and activity coefficients and all that. So in this lecture, I will talk further about those k values before coming to the idea of cascades, which I will develop further in the coming lectures. So what we have discussed in the last lecture is that this phase equilibrium ratio we can define, which is the ratio of the mole fraction of the vapor and the liquid for a particular component I, let's say yi by xi, which I will typically call as the k value for a vapor liquid equilibrium. In fact, we can define a similar quantity for other equilibria as well, as we will discuss. This quantity can be expressed in terms of the partial fugacity coefficients, basically the ratio of the partial fugacity coefficient of the liquid and the vapor, which has to come from the equation of state. However, in the case of liquids, it is more convenient to work in terms of activity coefficient instead, and in that case, we can write also as a ratio of the activity coefficients, right? Now, clearly, if I am using the partial fugacity coefficient, it is more appropriate for the vapor by the logic which I give, but not appropriate for the liquid. Or I can use activity coefficient, but it is more appropriate for the liquid, not so appropriate for the vapor. So I can also, for example, use activity coefficient for the liquid phase and the partial fugacity coefficient for the vapor phase. And in order to derive the relation, we can go back to our earlier relations. So basically, starting from the chemical potential equality and the fact that my partial fugacity was given as C exponential mu I by RT, basically I can express the chemical potential equality as the equality of the fugacities, partial fugacities in vapor and liquid. The partial fugacities can be expressed in terms of the partial fugacity coefficient for the vapor phase into YIP, and for the liquid I is expressed in terms of the fugacity of the pure component in the mixture at the same pressure multiplied by the activity, and the activity I can express in terms of the activity coefficient multiplied by the mole fraction. So therefore, that Ki can now be written something like this, that is a combination of the activity coefficient and partial fugacity coefficient. So now we are using activity coefficient language for the liquid phase and the partial fugacity coefficient language for the vapor phase. And if you think about it, this Fi naught by P can be thought of as the fugacity coefficient for the pure component, because the fugacity coefficient, the partial fugacity coefficient is defined as the ratio of the partial fugacity by the YIP. So for the pure component, we can define fugacity coefficient, which is going to be Fi by P, because for pure component the mole fraction is going to be equal to 1. So Fi naught by P I can write as phi IL without the over bar. That means that I am referring to a pure species, and I can therefore write it as something like this if I please, right? Keep in mind that we need not get confused by this language. Eventually all these relations are coming from the equality of chemical potentials only. The only reason why I am discussing them is because in literature sometimes the equation of states are expressed in terms of the partial fugacity coefficient for the vapor and the activity coefficients for the liquid, right? So therefore, whatever relation that we have available, we can directly use it here. Otherwise, it will require some kind of a derivation starting from the chemical potential equality, right? So these relations are available, and I don't expect you to remember all the formulas. You should be able to derive it starting from the chemical potential equalities. So therefore, as we have discussed, there are some rigorous forms of this k value. For example, I can express them as the ratio of partial fugacity coefficient or something like this, which I just derived. And then there are some approximate forms which are going to apply for particular situations. For example, if Raoult's law is valid, in that case Ki can be written like this, where Pis is the vapor pressure of component I in saturation conditions. We also have modified Raoult's law, where an extra activity coefficient also appears. We have something known as an additional Poynting correction and something known as the Henry's law that is applicable for dilute solutions. And in fact, there are many other approximate forms, right? So the key idea is that we are going to basically get this Ki from thermodynamics, right? If any of the approximations given here are valid or are appropriate, we can use one of these. If not, then we will try to get the detailed correlations for the partial fugacity coefficient or the activity coefficient, as the case may be, and tend to use the rigorous forms if approximate forms are not sufficient for the particular case that we are looking at. So as I said, I can also define this k value for other kind of equilibria. Let us say for a liquid-liquid equilibria, we can define something known as a KDI, where D is typically referred to the distribution, and this quantity is called the distribution coefficient or partition coefficient. And now it is the ratio of, because both the phases are liquid, so it is the ratio of the mole fraction of I in phase 1, the liquid phase 1, and mole component of I in liquid phase 2. Of course, the two liquids has to be immiscible in order to make a liquid-liquid equilibria, right? And again, I can express this xi by xi2 in terms of the activity coefficients, and we can essentially derive the corresponding relation. And if we are interested, we can also define in terms of partial fugacity coefficients. But for the liquid, activity coefficient is actually making more sense, so we will kind of use this more often. Okay. So next, we come to the idea of these cascades, which are basically aggregates of the separation stages, right? In the earlier class, we discussed about sequences of the separation stages, but there the idea was, the sequence was to basically separate multiple components of the mixture, right? In this particular case, we don't want to separate multiple components. We are using multiple stages just to make the separation process more efficient, so as to speak. That's the fundamental difference between the sequences that we have defined in the last class and the cascades that we will discuss. So cascades are something similar to what we had for the case of multiple effect evaporator. So my whole purpose remains the same as the single effect, but I want to basically get more efficient separation by introducing more effects, right? But the sequences is to separate more components out by introducing multiple columns. So the fundamental advantage is that we can now accomplish difficult situations, difficult separations. We can reduce the requirement of the MSA and ESA, and we can therefore have a more efficient use of raw material. As we have already seen, in the case of evaporator, the MSA was steam, and the steam requirement drastically reduced by using multiple effect evaporators, right? But then the same idea may apply to distillation process or whatnot. So these cascades we are going to play with are going to basically reduce the requirement of the MSA or ESA. And you can imagine that the MSA or ESA both are expensive. Energy comes at a price. Absorbent or whatever I am using also comes at a price. So basically, if I can reduce the need for that, it is going to increase the efficiency of the separation process. Right. So what I am showing here is an example of a counter current cascade, where the feed comes from top, passes through these 4 stages. The mass separating agent flows in the reverse manner like this, and one product is collected from the top and one from the bottom. It's like a counter current cascade. In general, you can have many other possibility. You can have a counter current cascade. You may imagine why not co-current cascade. In fact, we will do one example in the following class to see that why we are not doing a co-current cascade. In the counter current, as we said, one stream is flowing like this, the other is flowing in the reverse direction. We can have a cross current cascade where the steam and the streams flow across each other. So the products are collected from each of the stages in there, and the feed basically keeps on moving in this direction, right? That's one more example. And in this case, now we are forming 4 products as opposed to 2 products in this case, right? We can have more exotic configurations of cascade, let us say a diamond here, depending on the need and depending on the requirement of efficiency, as we will see. Okay, we can also have 2-section counter current or 2-section cross current cascades, right? For example, here the feed comes in the middle, and now we can think about the section above the feed line and section below the feed line, and the 2 sections are going to basically behaving differently, what is above the feed and what is below the feed, right? And again, we can have the one of the stream, maybe an MSA coming from the top and another MSA coming from the bottom, and we can have again 2 products going out, right? So the fundamental difference from the single section one is now we have a feed stream coming in the middle, and then there are 2 MSA stream coming from top and bottom. Now we can interlink them in a variety of ways. So I'm showing an interlinking of 2 different 2-section cascades in a quite complicated kind of a fashion, which can also be required for a particular applications. Okay, so let us begin with one example of a cascade that is for a leaching operation, right? So we have a solid liquid cascade where we want to basically leach out the soluble component from a solid feed, right? So in this case, the solid feed is coming here, and let us say Fa is the mass flow rate of the insoluble component A, and Fb is the mass flow rate of the soluble component B. There is a solvent that is basically taking away the soluble component, but the solvent enters the last stage, and the mass flow rate of solvent once it enters is some S, and this insoluble component along with whatever soluble component is left is basically flowing through what is known as the underflow, and the solvent carries the soluble component in the top stream in the counter current direction, and that is called the overflow, right? So the underflow essentially is some kind of a slurry, because the solid gets kind of, it will take up some water or whatever solvent is there, but it will get depleted of the soluble component, and the overflow will remain more or less a liquid. It will carry the soluble component along with that. So the soluble component will essentially dissolve in the solvent, right? So now let us define the mass flow rates Fa, Fb and S. Fa for insoluble, Fb for soluble, and S for the solvent that is coming in, the fresh solvent that is coming in. And now we can define a quantity xn and yn, xn for the underflow and yn for the overflow. That is essentially the mass of the dissolved B with, with the divided by the mass of the solvent, and that is solute free solvent, right? So whatever solvent C is coming here, that solvent will actually mix up with some B. So if I look at only the mass of C that is present in the solvent, that's the ratio I am looking at, right? So the mass of dissolved B and mass of the C that is in the solvent in the underflow for the case of X and in the overflow for the case of Y, and it is leaving the stage n, that is my xn. So this is my stage small n. So what leaves out of this is xn, that is moving in the towards the right, and yn, that is moving towards the left, and the compositions, the mass fractions is with reference to the mass of the solute free solvent. So now we can do first the material balance over the solvent, but before we do that, we define one other quantity. So keeping in mind that my solid feed will also take up some solvent, right? We can define a quantity R, that is the mass of solvent divided by the mass of insoluble solids in the underflow, right? That is the amount of water which is getting absorbed by the solid, right? And we assume that this quantity remains constant. It is a measure of some sort of a solubility or absorption capacity of the of the solid feed that is coming in, and mostly the insoluble component, because it is basically retaining some water along with it, right? So an insoluble component anyway is not going in the overflow, so the insoluble component remains constant, that is my Fa. So R into Fa therefore becomes the mass of solvent in the underflow, right? So of course, once it is entering, here the mass of solvent is initially 0, but then as soon as it leaves the first stage, it forms some kind of an equilibrium. We assume that every stage in some kind of an equilibrium. So it forms some kind of an equilibrium here, and what leaves out of this contains Rfa, mass of the solvent, right? And the same is true here, and same is true for all the stages in the underflow, and the same RFA is also going to leave the nth stage. So whatever solvent gets in the solid gets absorbed there, that solvent remains there in the same amount until the end of the process, right? On the other hand, the solvent is going to take up the soluble component B in the overflow along with it, right? So if I now look at the amount of solvent in the overflow, in the very first stage for the solvent enters the nth stage. So when it is entering, the mass flow rate of solvent is S, and for the nth stage, for the underflow there is no change. The RFA solvent came and RFA solvent left. So same S basically gets into the n minus 1th stage, and same S keeps on moving in the overflow until it reaches the first stage, right? In the first stage, the feed contains no solvent. The feed contains no solvent. So basically, out of this S that is coming in, the solvent that is coming in, RFA basically goes out in the underflow, right? So if I do a mass balance over the first stage, then the solvent that is coming in is S from the overflow, and solvent leaving the underflow is RFA. So basically S minus RFA is going to be the mass flow rate of solvent leaving the first stage, right? So for the overflow, all except the first stage is going to have the mass flow rate S of solvent, and for the underflow, all except the feed is going to contain RFA of the solvent. So once we have done the solvent material balance, we can also do the material balance for B for intermediate stages between n equal to 2 to n minus 1 first. The same thing I will do for the terminal ones also, right. So here what is coming in for B? So y n plus 1, basically y is a ratio of the mass of B by the mass of solvent, and mass flow rate of solvent is S. So y n plus 1 S basically is the mass of B entering stage n coming from here from overflow, and now there is also a mass of B coming from the underflow, that is right here, but that is coming from the n minus 1th stage, right. So x n minus 1 is the ratio of the mass of B to the mass of solvent in the underflow, and mass flow rate of solvent in the underflow is RFA. So the product is going to be mass of B entering stage n from underflow, right. Now the similar thing I can do for what is going out of there. So xn into RFA is basically the mass of B leaving stage n from underflow, that is right here, and this is the mass of B leaving stage n from overflow. So we essentially did in equal to out for the amount of B. So we added what enters from the overflow, what enters from the underflow, that makes up the left hand side, and we added what enters, what leaves the overflow and what leaves the underflow, that makes up the right hand side, and we equate them and we get the material balance for B. Now for terminal stages we have to be slightly careful, because let us say for the first stage in the overflow, in the overflow what comes in has solvent mass flow rate of S. So we have Y2S, this is in from overflow, but what comes in from the underflow, it is not containing any solvent. In fact, it contains some mass flow rate B of soluble, FB of B, right. So this is the mass flow rate of B that is coming in, that is equal to FB. So it is the in the underflow. Now for the out, as we have discussed when we did the material balance for the solvent, what leaves the stage 1, it has a mass flow rate of S minus RFA. Every other stage in the overflow has a mass flow rate of S, but what leaves the first stage has a mass flow rate of S minus RFA. So that's why we multiply Y1 with S minus RFA. This is out in the overflow, and the out in the underflow is X1 into RFA. We can go ahead and do the same thing for the nth stage. Again, in the overflow there is no B entering because we have fresh solvent entering. So the first term is not there. The in from the overflow is essentially equal to 0 here. So we only have the in from the underflow, and what is leaving now of course contain B. So this is the out from the overflow, and this is the out from the underflow. And finally, we can use the condition of equilibrium that states that my xn should be equal to yn. Why is that? Because B, we are talking about the solubility of B in a solvent, right? So the x and y are defined as the mass of B by the mass of solute free solvent. So in a condition of equilibrium, this quantity will refer to some sort of an equilibrium solubility of B in the solvent, and that is going to be the same in the overflow and the underflow, right? Whether the equilibrium will be attained or not is a separate story, and we will talk about it later. But in all the separation processes we are going to discuss, mostly we are going to assume that we have a condition of equilibrium. So in that case, xn is going to be equal to yn, and if I basically plug it in my earlier equations, you can see we get equations like this. So let us start from the first equation here. If I put y equal to x, we are going to get something like xn plus 1 s plus xn minus 1 rfa is equal to xns plus xn rfa, and we can divide this quantity by rfa, and we can get something like xn plus 1 s by rfa plus xn minus 1 is equal to xn s by rfa plus xn. And now we can note that this particular quantity can be given some name, and I am calling it the washing factor W, that is the ratio of the fresh solvent mass flow rate and the RFA, right? And then we are going to get the corresponding equation as something like this after some rearrangement, right? And the same thing we can do for whatever mole balances, mass balances we had for the terminal stages, and we can get basically a simplified system of equation, which happens to be a tridiagonal system of equation, right? And then we can essentially solve it using the methods which we implied for the tridiagonal matrices. So after solving this, we can, I will not derive the complete expression, but we get something like this. So xn is going to be fb by s sum over k equal to 0 to n minus n wk by wn minus 1, where w is my washing factor, right? Now it also sets the minimum possible value of the mass flow rate of S, and that is going to be my RFA, because when S is equal to RFA, then the overflow leaving the first stage is going to be 0, right? So the minimum possible value of S has to be RFA. S cannot be less than that because you cannot have a negative value there, right? But if that happens, then the solvent essentially is not carrying anything out finally. Ultimately, I want the solvent to carry the soluble component along with it, right? But if S is equal to S min, then the overflow has a 0 mass flow rate, right? So that is not really a desired circumstance. So we will typically want to have my S value more than this minimum possible value, more than this RFA value, in order to have an efficient separation, right? So with that, I conclude the discussion on the solid liquid cascade. We will take some examples in the next lecture. So with that, I conclude here. Thank you so much.